rigid rotator. So chapter 6 is the rigid rotator and rotational spectroscopy. So in the previous chapter, chapter 5, we learned the harmonic oscillator. And the harmonic oscillator is the toy model for describing the vibration motion, and it is really well describing the vibration motion of diatomic molecules. And chapter 6 is about the rotation motion, and the rotation motion can be well described with the rigid rotator. And as the name implies, the rigid rotator means the distance between two atoms is fixed. So we are not considering the effect from the distance changes. And as we discussed in the previous chapter, the vibration motion has the frequency falling in the infrared region. And the rotation motion, the speed of the rotation motion falls in the rotational spectroscopy, which is about the microwave region. So vibration can be described by the harmonic oscillator. And its frequency is in the infrared region. And chapter 6 is rotation motion, and this is described by the rigid rotator. And this corresponds to the microwave region. Okay, let's start. Section 6.1. The title is the energy levels of So chapter 6, section 6.1 is about the energy levels of rigid rotator, and the title already gives you the quantized energy level of rigid rotator. So here J is the rotational quantum number, and this can be 0, 1, 2, like positive integer with 0. And I is the moment of the inertia. So rotational energy level is given like this, and we are going to try to understand why the rotational motion gives such quantized energy level. So before we beginning, we need to understand the rigid rotator model. So we are going to discuss that one first. Rigid rotator model. So it looks very similar to the previous diatom model. And there are two mass. The first one with mass M1 and the second one with mass M2. And their distance between them is L. And we can always determine the position of the center of the mass. So let's assume the center of mass is placed here. That means the distance between the first particle and the center of mass would be L1. And similarly, we can define L2. Okay. So these two particles or these two atoms are rotating with respect to the center of mass. So let's say they make a rotation like this, and the center of mass is placed here. And let's assume that these diatom molecules rotate about its center of mass at a speed or at a frequency of nu rot. So this means this diatom molecule make a rotation nu rot times per second, right? So this means how many rotation does this molecule make in 1 second? So you can determine the velocity of these two masses. So we want to know the velocity v1 and v2. So it should be defined like 2 pi L1 multiplied by the angular velocity nu rot or angular frequency nu rot. Similarly, the second mass or second particle has the velocity like this. And we can introduce the angular velocity. So angular velocity is defined as 2 pi multiplied by the angular frequency. So that means L1 omega 1. And similarly, the velocity for the second particle can be defined as L2 multiplied by omega 2. Oh, sorry. So there should be 1 omega here, right? So even though they have the different velocity, their angular frequency and the angular velocity should be same because they are rotating as a one body. And from this relation, we are going to define the kinetic energy of the rigid rotator. So kinetic energy T is simply the sum of the kinetic energy of each particle. So half of the m1 multiplied by v1 square, m2 v2 square. And we already know the expression for the velocity 1 and velocity 2. So they are given here. So let's plug this expression into the kinetic energy expression. And you may notice that the term in the parenthesis, this corresponds to the moment of inertia, right? We already discussed that in the chapter 5 when we talk about the harmonic oscillator. So final expression would be like this. And we can simplify this equation further. So let's take a look at the expression for moment of inertia I. So from the relation between the center of mass and like the distance between L1 and L2, we know that M1 multiplied L1 should be equal to M2 multiplied by L2, right? This is the definition of the center of mass. And when we introduce this relation into the moment of inertia, then we can simplify the moment of inertia like reduced mass multiplied by L square. So we already discussed this technique, right? So if there are two bodies and two bodies can move freely, we can introduce the reduced reduced mass to simplify that problem. Like two-body problem can be converted into one-body problem. So with the reduced mass mu. So during this procedure, we replaced this two-body problem into one-body problem, where the other end is fixed. So this is fixed, and every physics is exactly the same. And so we would like to define the angular momentum. Angular momentum, capital L. This should be the moment of inertia multiplied by the angular velocity. And we know that the kinetic energy is defined as the L square, the square of the angular momentum divided by 2I. So this is very fundamental relation, and I guess we already discussed that one in the chapter 5. So please pay attention to these two relations. And we can assume that there is no potential energy term because we are discussing the rotation in the absence of the external force, right? So we are not considering any magnetic field nor the electric field or gravitational field here. So we focus on the rotation motion, and that means we are only dealing with the kinetic energy. So in the absence of the potential energy, then the Hamiltonian operator is simply the kinetic energy operator, or let's just say kinetic energy operator T, right? So based on the definition of the kinetic energy operator, so here we introduce the Laplacian operator. This is Laplacian operator. So this is simply take the second derivative with respect to x, y, and z direction. So in the Cartesian coordinate, the Laplacian operator is given like this. But here we are discussing the rotation motion. So rather than the Cartesian coordinate, the spherical coordinate is better option. So we are going to use the spherical coordinate. So in this coordinate, rather than x, y, z, we are going to use r, theta, and p. So I guess you are very familiar with this coordinate, so I'm not going to talk about this system again. I will not discuss that one in here. So, but okay. So then what about the Laplacian operator in spherical coordinate? Because we have to know the explicit expression of the Laplacian operator in the spherical coordinate, because we want to understand and we want to calculate we want to solve the Schrödinger equation in the spherical coordinate. So this is very long derivation and tedious mathematics, so we are not going to talk together, but if you are interested in, then you can take a look at the problem 6 exercise problems 6-2 and 3. So these two problems introduce the detailed procedure of how you can convert the Laplacian operator in the Cartesian coordinate to the spherical coordinate. So let's just accept the final result. So it's 1 over r squared. So this is quite long expression. I'm going to make some comment about the partial derivative. So the first partial derivative is about the position r or the length r. And during this, I make a mistake here. So while we are taking the derivative with respect to the distance r, we need to fix the two angles, the theta and p should be fixed. So this subscript denotes which variables are fixed during the differentiation. And the second term is about the angle theta. So angle theta is defined the angle between the x-axis and your xy projection. So if you have in xyz coordinate and there is an arbitrary point here, and you can always calculate the distance between the origin and your interest. This is r. And you can think about the projection onto xy plane. So this is angle theta. And the final derivation is about p. So p is the angle between your point and the g-axis. Okay. And as we mentioned, we are talking about the rigid rotator. That means the distance between two particles should be fixed during the rotation, right? So that means dr should be 0, right? So we don't really have to take care about the differentiation with respect to r. So that means we don't really need this part because this part will vanish. That means, and we can fix the distance as r, distance r as the length L. So L square sine theta. So this is the second term of the original expression, this expression. And we also have the final expression. So we don't really need the subscript r here anymore because we are fixing the distance. So the distance is no more variable. They can be considered as constant, so we don't really need to explicitly showing that r is fixed during the differentiation. So this is the spherical, the Laplacian operator in the spherical coordinate form. with the assumption of rigid rotator. So that means the Hamiltonian operator is simply the h bar square over 2I multiplied by the Laplacian operator, and the Laplacian operator is given like this. So you now have the Hamiltonian operator in the spherical coordinate form. Okay, and unfortunately, solving this Schrödinger equation takes a lot of time, and it requires some knowledge in mathematics, which is beyond the scope of our course. So we just accept that the solution of the Schrödinger equation for this Hamiltonian shape is given as spherical coordinate y. Spherical harmonics y. And spherical harmonics is characterized by two variables, the zeta and p. This is spherical harmonics. So even though we are not going to solve this Schrödinger equation, but actually we can, I might be wrong. So actually we are going to solve this Schrödinger equation. I got confused, sorry. So we are going to simplify this expression and with some mathematic treatment. So let's say we have, so I'm going to rewrite the whole expression again. So the left-hand side, this highlighted with the yellow line, this is the definition of the Hamiltonian operator. So we are going to multiply the whole equation by sine square, multiplied by sine square, and let the beta as the 2I multiplied by energy divided by the reduced Planck constant square. And that will give you the much simplified expression, the sine zeta, d zeta So this is simple mathematics, so you can do it by yourself. So this is the differential equation that we want to solve. So as you may notice, our solution contains two variables, zeta and zeta and p, and they are independent variables, right? because we convert the xyg to r theta and p, that means there is no intercorrelation between them. So r theta phi, r theta p, they are independent variables. That means we can apply the separation of variables to this solution. So r theta p can be expressed as the largest theta multiplied by large p. Again, you can substitute this result into the original differential equation. And then you will have the sine theta divided by large theta, dd theta, large theta. So I usually put H for the capital theta. So because they look very similar, the small theta and capital theta, they look nearly the same. So if we want to differentiate them, distinguish them, then let's use the H here. So because the theta and p, they are independent variables, that means the only way, this part, these two terms are involved with theta, and the last term involves only with p. So if the equation involving two different independent variables to be zero, that means that they should be equal to some constant number, right? So in that case, we are going to define, like, equate. The theta term should be equal to m squared, and that means the term involving the p should be equal to minus m squared. So by applying the separation of variable technique, we decompose the one complex differential equation into two independent differential equation, right? So the first one is this one, yellow box, and the second one is the green box. So now let's summarize what we have done so far. So we are discussing the rotation motion and using the rigid rotator model, and we define the Hamiltonian operator in the spherical coordinate and applying the separation of variable techniques because the theta and p are independent variables. So we can make a fragmentation for the one complex differential equation. So now we have two differential equations here. So let's take a look at the second expression first, because this differential equation is much easier to solve compared to the first one. So 1 over capital P square should be equal to minus m square. So this is very well-known linear differential equation, right? So you want to take the second derivative of your solution, and that should be equal to the some constant multiplied by itself. So this differential equation can be satisfied with exponential function, right? But now you have the minus m square here, which means that the value should be the negative. So you need to introduce the imaginary number. So the first possibility is the normalization constant am multiplied by exponential im p. And the second possibility is a minus m exponential minus im p. So both of them can satisfy this differential equation, right? Because we are dealing with the m square here. M square is the constant value here. So that means that both m and minus m can satisfy this differential equation. And we need to find some condition for the constant value m. So the first condition that we can come up with is the wave function should be a single valued function, right? Wave function should be single valued, because the square of the wave function is related to the probability. So wave function should have only one value at the specific point. And as you may notice, the exponential imp, this is according to the Euler's formula. This is simply the cosine mp multiplied by I sine mp. So that means the exponential imp, this function is periodic function, right? Because it is consisting of the real part of the cosine function and the imaginary part of the sine function. So it is periodic function, and so the value of p at capital P at small p, this should be equal to the p plus 2 pi. Because this is simply the summation of the cosine and sine function. So from the single valued condition, we can derive the first condition for the wave function. So am eimp, this should be equal to am exponential I m p plus 2 pi. And you can write a similar expression for exponential minus imp, right? A minus m should be equal to So from these two relations, we can claim that exponential plus or minus I multiplied by 2 pi m should be 1. So as I mentioned, the exponential to I multiplied some variable, this can be expressed with cosine and sine function according to Euler's formula. Cosine 2 pi m multiplied by sine I sine 2 pi m, and this should be 1. So this equality should remain always, right? That means we don't really need the imaginary part. We need to remove the imaginary part. So the only way that can remove the imaginary part, the sine term should be 0. And how to make the sine term 0 with the variable m? So we can just take the integer multiplies of the integer, like 0 plus minus 1 plus minus 2, etc. So you might notice we have another quantization here. So m value cannot have the arbitrary value. So m value should be the integer value, 0 plus minus 1 plus minus 2, etc. Only these values are allowed, and other values cannot be used for describing the rotation motion. So now we know the condition for the constant or the parameter m. And still we don't know the form of this normalization constant. Normalization constant. So this is discussed in the example 6-1, but we are going to take a look at together. So it is always about take the square of the wave function, and you are going to integrate that function and equate the result to 1, because that is related to the probability. So you are going to multiply, you are going to, let's take the square. That means we are dealing with the imaginary number, so that means take the square is exactly equal to the multiplication between the complex conjugate and its original function. So this is related to the probability density, and you are going to multiply it by the volume element, the infinitesimal volume here. So you are going to integrate all the probability from 0 to 2 pi, and that should be equal to 1. So the capital P, it looks like AM multiplied by EIMP. So if you take the complex conjugate and multiplied these two numbers, this is simply the AM square and this is just a constant that doesn't depend on the P, variable P. So AM square d pi dp, that means multiplied by 2 pi should be equal to 1. So we can say that the normalization constant should be 1 over square root 2 pi. So this reveals the wave function in terms of the variable P. So capital P should look like 1 over 2 pi exponential IMP, with some restriction that m value should be 0 plus minus 1 plus minus 2, etc. Okay. And we are going to, so we derive the wave function for variable P. So the capital P looks like this. And we are going to introduce the rotational constant. So we define the beta while we try to solve the Schrödinger equation for the rigid rotator, which is given as the 2IE multiplied by h bar square. And maybe today or maybe this week Wednesday, so we will solve the Schrödinger equation for the rigid rotator. But before we try to solve that, we just accept the final result. And beta, this value should be given like this. So J should be 0, 1, 2, etc. So this looking random, like this looks very random, right? So you don't quite understand why the beta should be equal to J multiplied by J plus 1. Even though it looks very random, but we are going to derive that relation later. And from now, we just accept that, okay? So from this relation, you may notice that energy value is also quantized, right? So energy level EJ is given as the h bar square divided by 2I and J plus 1. So we are going to introduce the rotational constant here. So rotational constant is the h bar square multiplied by 2I. So rotational constant is given as B. So this is all about the simplifying the expression. So there is no really physical changes during this notation change. So this is the energy level, allowed energy levels for the rotation motion. And we can also discuss the degeneracy. So we saw that the energy is dependent on J, right? Energy is the function of J. But actually the the quantum number M doesn't appear here, which means they don't really affect the allowed energy levels. And for M, the allowed M value is from minus J to plus J. So that means the degeneracy of J energy level, Gj, this should be 2J plus 1. So if you feel that something is missing, like why do we have the M number between minus J and J, all that your concern or all that your curiosity will be addressed maybe the end of this lecture or in the next lecture. Okay, anyway, we summarized the final result of the rotation motion, and we are going to move to the next section. Okay, section 6.2, the title is the rigid rotator is a model for a rotating diatomic molecule. So we already discussed that one in the introductory part, but let's take a look at and let's try to calculate the energy levels, and let's see if the rotating motion really describes the rigid rotator can describe the motion with the frequency region of the microwave. Okay, so let's not assume what textbook said. Let's verify it. Okay. So first, we are going to take a look at the selection rule, because if we want to calculate the transition energy, we always have to know the selection rule allowed the transition level. And this will be discussed in the section 6.7, but let's just accept the final result. So in the rigid rotator, the allowed transition is delta J plus minus 1. And of course, the molecule must also possess a permanent dipole moment, right? So this is the first rule, and the permanent dipole is required, right? So this is very similar to the selection rule in the harmonic oscillator. So you might remember that in addition to the adjacent energy level transition, the molecule should have the permanent dipole, right? So I missed the O here. Dipole moment. So anyway, with this selection rule, and we are going to calculate the energy difference, delta E. So let's assume that we are talking about the absorption. So the final energy level should be EJ plus 1, and the initial level should be EJ. And they are given as h bar squared divided by 2I, which is exactly the rotation constant. J plus 1 and J plus 2, because for here, the value is the J plus 1. So J plus 1 here, and J plus 1 should be J plus 2, right? Minus J plus 1. Right, so here is J, and J plus 1. So we have the common term J plus 1, and the final result should be I squared, h bar squared divided by J plus 1. Okay. And if you want to restore the Planck constant from the reduced Planck constant, h bar is the Planck constant divided by 2 pi. So 4 pi square I over h squared divided by 4 pi square I, J plus 1. So when I was an undergraduate student, I don't really like this microwave spectroscopy, because there are too many notations. So in some textbook, and like the energy level difference is like this, and some textbook like this. So of course I know that I can convert from the left to right, right to left, but it always makes me confused. So you always have to pay more attention not to confuse between these very looking similar expressions. And anyway, we have a important observation. So energy level, let's write the final expression here. So energy difference in the rotation motion, it is proportional to J, right? Energy level J. So that means for j equal 0, so we have the energy here, and j plus 1, you have the energy level here. For j equal 2, you have energy level here, and j equals 3, you have energy level here. So what does this mean? So energy level between the adjacent energy difference between the adjacent energy level gets larger and larger with the increasing quantum number j, right? So so here the energy level should be 4h squared divided by 4 pi square I, and here multiplied by 2, and 4. Right, so you notice that energy levels gets increased with the quantum number j. So this is very different from the harmonic oscillator, right? So for the harmonic oscillator, energy level is given as the h omega v plus 1/2. So that means the energy difference between the adjacent level should be given as h bar omega. So energy levels are constant, right? So from 0 to 1, 1 to 2, 2 to 3, the energy level difference is always constant. But what about the rotation motion? So energy level gets larger and larger. So in the harmonic oscillator, you will have the only one peak along the frequency, so like here. But what about the rigid rotator? So energy level J is P multiplied by J and J plus 1, delta EJ, 2BJ, like this. 2BJ plus 1, sorry. So that means in the rotational spectroscopy, you will have like 2B here, 4B here, 6B here along the J level. So you will have the multiple peaks in rotation motion. Okay, and so we already calculate the energy difference here, right? We have the energy difference for the rigid rotator model, and we know that during this transition, the molecule can absorb the photon, or molecule can emit the photon, and the absorbing or emitting photons energy level should correspond to h nu observation, so the frequency of the photon. So this, let's say, so this is the energy level difference in the rigid rotator, and this is the energy of the observing photon. So the frequency of the observing photon should be h square I j plus 1. So when we say the microwave is responsible for the rotation motion, so if you calculate the new observation from the this relation, this value falls in the microwave region. So let's say that in the typical situation, the reduced mass of the diatom molecule is like 10 to minus 25, 10 to minus 26 kilogram. And the typical bond distance is like, let's say, L should be 100 picometer. So this is the typical bond region of the covalent bond. So from this value, you can calculate the moment of inertia, right? This is simply the mu multiplied by L square. So from this value, you can calculate the new observation, right? So this is like 10 to 10 hertz, 10 to 11 hertz area. So this is about the microwave region. That's why we say that the rotation motion is related to the microwave spectroscopy. So this is quite obvious example. Okay, let's move on to the next section. Okay, section 6.3 is about the rotation motion with vibration motion. So in reality, we cannot really separate the vibration motion and the rotation motion because they are working together, right? So some molecules are rotating while their bond distance are elongated or stretched, elongated or the compressed. So usually they occur together. So we are going to say that rotational, vibrational motion. So we can describe the vibration motion using harmonic oscillator, and we can describe the rotational motion using rigid rotator. So simply, the allowed energy level with the quantum number V and J should be V plus 1/2 H nu plus B J plus 1. So for the spectroscopist, they always prefer the wave number unit rather than the energy level, energies. So we try to convert the energy to wave number. We want to express the energy in terms of the wave number unit. So we put tilde here to explicitly showing that this is given in terms of the wave number unit. So all you have to do is just divided by Hc to convert the energy to wave number unit. So that means divided by Hc should not affect the quantum number. And omega tilde, and we have the B tilde J plus 1. So omega tilde here, this is simply the angular velocity divided by c. And the B tilde, this is 4 pi square Ci H. So what I want to emphasize here is if you calculate the calculate the omega tilde. Omega tilde and B tilde. This is like the metric of the energy levels for vibration motion and rotation motion, right? Because they are proportional to some quantum number here, right? So if you calculate the omega tilde and B tilde for typical molecules, then you will realize that the order of the omega tilde is like 10 to 3 wave number, centimeter inverse, and the B tilde is only about the 1 wave number unit. So you might notice that the vibration energy level, this is about 100 or 10 times, 1,000 times larger spacing compared to the rotational motion. So like when you draw the potential energy surface like this, so there is a rotation motion like here, like this. So, vibration motion. Nu equal V equal 0, V equal 1, V equal 2, and they are equally spacing. H nu. And the rotation motion is, the spacing in the rotation motion is only about 100 or 1,000 times smaller. So that means the rotation energy level is something like this. And from here, something like this. So this, even though it looks continuum, so if you enlarge this area, the energy levels are really compactly spaced. So they look like nearly continuous level in term compared to the vibration energy levels. Okay, so infrared region is much higher energy region compared to the microwave region, and the energy spacing is quite different. And we are also going to discuss the P branch and R branch. So this is not really, this is just the terminology for the various peaks in the rotational vibrational spectroscopy. So let's take a look at selection rules. So we are now dealing with the vibration and the rotation motion together. So for the vibration motion, delta B should be plus minus 1, and delta J should be plus minus 1. So as I mentioned, the vibration energy level has much larger energy spacing. So we assume that okay, so let's just calculate the observed frequency for delta J equal to plus 1. And you can just calculate the this one. So this is the summation of the vibration and the rotation energy level, and this is 2. So you will easily realize that, so for the allowed vibration energy, so here should be V plus 1, right? V plus 1 and J plus 1. So the final result should be omega tilde plus 2B tilde J plus 1. And for the transition with delta J equal to minus 1, then we have the So here basically we are discussing the transition from B to B plus 1, right? B to B plus 1 and B to B plus 1. But the difference is the rotational energy level. So we are starting with J level. So the first set of the peak is the rotational absorption. So J to J plus 1. So that means you are starting the J level here, and you are going to excite this molecule into J plus 1 on the V plus 1 harmonic oscillator surface. So J plus 1 here, somewhere here. Then what about we need different color. What about the second set of transition? So you are dealing with the transition from J to J minus 1. So you are starting here, same, but now you are exciting to the lower energy level, J minus 1. So even though I use the J and J plus 1 and J minus 1, but they are not belonging to the same energy level. I mean, they are on the different potential energy surface. So let's redraw the figure. So let's say B equal 0, B equal 1. And there is a small spacing rotation energy level here. So the first set of transition describes J here. So maybe J equal to 1, but J equal to much higher region, from here to here. So vibrationally excited, right? V equal 0 to V equal 1, vibrationally excited. And in terms of rotation, it is also excited, right? So second allowed vibrational excitation, a rotational excitation to like J equals 6 level. If I want to be more precise, the energy level of the J should be increased, right? Something like this. Anyway, so J here. The second set describes the from here to here. So originally it was in the J equal 2, but after the excitation, now it is in the J equal 1 energy level. Okay, so these two subscripts working together. So please do not get confused. So the final expression for this one is 2 minus J. So when you take the IR spectrum, if the molecule doesn't really rotate itself, then you are going to only have the one vibrational energy level, like here, one vibrational energy level. But always the molecule always rotating and vibrating together. So you are going to have the in addition to the omega tilde, you will have the further energy level transition, so their energy level spacing should be all equal to 2b tilde. This is called R branch. And for the second set of the transition, so in addition to the fundamental peak, omega tilde, you will have some rotational de-excitation energy level here. So all the spacing should be 2b tilde 2. So this is called P branch. Okay, actually, so I put the pure IR spectrum transition here, but actually this peak shouldn't appear. Can you discuss why? Even though this peak describes the transition from B to B plus 1, this one involves the transition from J to J, right? Because this describes J to J plus 1, J plus 2, etc. J minus 1, J minus 2, etc. That means the middle peak, that one should be J equal J. So even though it is allowed within the harmonic oscillator, this is not allowed in the rotation motion, right? So this peak is not observed in the real molecule.